Hi, my name is Konstantinos, and today I'd like to talk a little bit about a system we're building here at the University of Maryland called GraphGen. We've seen that analysis of interconnection structures such as graphs can provide very valuable insights. However, for various reasons, the most common ways of storing data is currently not in native graph stores. So in order for users to apply these graph-based analyses, they need to go through a tedious, unintuitive process of manually querying the data and properly transforming the result into a graph format. Also, the average dataset can contain a large number of potential relationships between many of its attributes, and it is thus not always clear which of these hidden graphs may prove to be of value. For example, on a DBLP dataset of authors and publications, we can connect two authors if they've co-authored more than n papers together, or if they've had a recent co-authorship. All of this creates walls that clearly hinder the adoption of graph-based analyses on datasets where they could potentially provide great value. In response to this problem, we're building a system called GraphGen that sits on top of relational databases through which users are able to declaratively express which graphs they are interested in analyzing. Using various optimizations, the declarative queries are translated into SQL that is then used to efficiently extract the graph in memory, where users are able to run custom Vertex-centric programs on top of it using our API. We've defined a declarative language based on datalog that allows users to write intuitive, short, and simple graph extraction queries. Users can write queries that range from extracting a single graph based on a bunch of conditions to a series of separate ego graphs, while also supporting simple aggregates like connecting two authors if they've co-authored at least 5 papers together. There are multiple approaches one can take when using GraphGen. One of them is using the GraphGen front end. This web application is geared towards providing exploration capabilities for when users aren't certain about which graphs may be interesting to analyze. First, the user can connect to a database by providing the database's location, connection credentials, as well as the name of the database to be loaded, and click Connect. The schema is then loaded into the web app, showcasing its primary and foreign key constraints in order to help users reason about the queries they can write. Next, the user can either manually specify an extraction query in the query text area or use the auto-generate button to get an automatically generated data log query for a graph of possible interest. This is made possible using our graph enumeration framework, which creates a schema graph based on the constraints that characterize a specific schema. Through paths or loops in this graph, we are able to generate potential graphs of interest. Clicking the Load Graph button will generate and execute the appropriate SQL and load the graph into memory, as well as generate some statistics about the graph, as well as plot the degree distribution of its nodes. By clicking the Fetch Sample button, users can explore the structure of the graph by fetching the one-hop neighborhood samples of either random nodes or by specifying a simple predicate. Users can also hover over the nodes in the graph to see the data associated with each node. When graphs are extracted and loaded into memory, some basic graph algorithms are automatically run against the graph through calculating node degree, PageRank, local clustering coefficient, and hit centrality. Using the node analysis pane, users can take a step back and explore the properties of the graph even further. For example, fetching the top 20 nodes based on descending node degree. It turns out that extracting these graphs is not always straightforward, which led to the development of various optimizations. Extracting graphs from relational tables often requires expensive self-joins that can end up being impossible to materialize as the table grows in size. One of the most important optimizations happening under the hood is that using the estimates provided by the query optimizer, we can choose to skip these self-joins completely and construct the graph in a condensed representation instead, which only requires a single sequential scan over the table. The condensed representation consists of real and virtual nodes. The catch, however, is that this representation now includes multiples of the same edges when nodes are connected to one or more common virtual node, which can impact the correctness of most graph algorithms. For this, we have developed a suite of algorithms for removing these duplicate edges while maintaining a level of compression as well as performance in the resulting graph. Once deduplicated, users can correctly execute Vertex-centric programs on top of these condensed graphs using our multi-threaded Vertex-centric framework implementation. So as a result, skipping this join not only makes the extraction possible, where the join couldn't have completed in a reasonable amount of time, but it also results into a smaller footprint condensed graph that is equivalent to the standard representation. Another optimization is when a user submits a query for extracting multiple ego graphs, instead of executing a series of single graph extraction queries, we can submit a single union query that constructs an array of tags as metadata for each edge. This metadata conveys which ego graphs the edge is included in, and thus allows for a 9x faster extraction of these graphs than the alternative. Another way to use GraphGen would be through our Python API for extracting graphs and serializing the graphs into disk for further analysis using other third-party libraries like NetworkX. Executing an extraction query in our Python API is also very straightforward. There is also a handy export graph button in the front-end web application that allows users to serialize the entirety of the extracted graph onto disk in a standardized format. Lastly, GraphGen can also be used through our native Java API, where users can easily connect to the database, write and execute an extraction query, as well as define and execute Vertex-centric programs on the extracted graphs. Our preliminary results show that the deduplicated condensed representation provides an equivalent but smaller footprint graph that allows for analysis with comparable performance of Vertex-centric programs. GraphGen is under active development, and some of the goals in our ongoing work include to systematically utilize the query optimizer for a more informed decision on when to skip self-joins and use the condensed representation, mitigating the limitations of query optimizers at selectivity estimation over complex queries with self-joins, coming up with more efficient algorithms for deduplication of very large condensed graphs, as well as have a series of language extensions to support expressing inline graph computation towards an end-to-end framework for graph analytics over data stored in relational databases.